Hi, my name is Ajay. Today, I'm going to do a presentation on the topic homomorphic encryption. The topics that I'm going to cover in this presentation are as follows. First, we will cover traditional encryption model and its drawbacks, followed by introduction to homomorphic encryption, then applications of homomorphic encryption, next, example of homomorphic encryption, followed by types of homomorphic encryption, next limitations of homomorphic encryption, and then at last with conclusion. So let's start this presentation. So traditional encryption model. When we say traditional encryption model, it refers to both symmetric and asymmetric encryption models. But for this presentation, let's focus on the asymmetric encryption process. So the steps in the asymmetric encryption process are as follows. The first step would be the plain text would be encrypted to a ciphertext using either a public or a private key, which in this case we have used a public key to encrypt the plain text into a ciphertext. So when the user wants to analyze or perform any computation, he or she first need to decrypt that ciphertext using the private or the public key accordingly. So this is the overall flow of the asymmetric encryption model. Now let's move on to the drawbacks in the asymmetric or in general the traditional encryption process. So the drawbacks are as follows. So the data must be decrypted before computation or before we perform any analytical tasks, which exposes the sensitive information, which creates a security threat. So the privacy risk when data is handled by third-party services like a cloud server or any web applications. It increases the attack surface, which is increases the risk of data leaks during processing, and it's not suitable for applications that demand end-to-end confidentiality. Let's move on to homomorphic encryption. So, what is homomorphic encryption? It is a cryptographic technique that allows computation to be performed on an encrypted data without requiring decryption. The output, when decrypted, is identical to the result of operations performed on the original data. So, it says it's a technique which allows the user to perform any mathematical operations on the encrypted data without requiring to decrypt and actually revealing the data, which is the case in the traditional encryption models. So how it solves the privacy issue exactly? Let's look into that. So as I said earlier, the homomorphic encryption doesn't require to decrypt the ciphertext before applying any processing or mathematical computation, which eliminates the exposure of sensitive information. It ensures confidentiality even during computation in untrusted environments like cloud servers or in web-based services. It helps us to achieve end-to-end data privacy. So let's look into how it works. So similar to the traditional asymmetric encryption process, the homomorphic encryption also begins with the generation of public and private key. So either a public or a private key is used to encrypt the actual message or the plain text, and we create a ciphertext. So this encrypted ciphertext is sent to the cloud services or the web servers to perform the mathematical computation or any operation. And after performing the mathematical operation, it gives an output which is also an encrypted text. So this encrypted text need to be decrypted using the private or the public key, vice versa according to the key that you have used to encrypt the message, will give the final output. Now let's look into the applications of homomorphic encryption, in which we would get to know what are the various fields in which the homomorphic encryption is getting used. So the first field in which the homomorphic encryption is being used is secure cloud computation. Traditional cloud-based computational methods require access to unencrypted data to perform computations, which exposes sensitive data to cloud operators and any malicious actors that breach the network. With homomorphic encryption, cloud servers can compute directly on encrypted data and return encrypted results to the owner of the data, who can then decrypt them manually. So the application of homomorphic encryption on the cloud computation platform made them a way more secure way to work with. By hiding what the exact data on which these platforms work with, the user can have the ensurety that their data is not being visible to the operators. Next is secure voting. So voters can securely cast their votes without ever having to reveal who they voted for. This could make elections fairer and more transparent, and the enhanced privacy could encourage voter participation. And then securing healthcare data sharing. In healthcare, this technique allows users to share patient data with healthcare providers or research securely. It enables collaborative research without compromising patient privacy. And a real life use case application of securing healthcare data sharing would be taken in the upcoming slides. Secure artificial intelligence or machine learning. So AI or ML algorithms can be trained on sensitive data without the raw data being exposed. This guaranteed data privacy can give large populations of individuals the confidence and security need to share their data with AI projects, providing them with huge volumes of raw data necessary to run AI algorithms that make a real-world impact. Many artificial intelligence and ML learning algorithms can be trained and developed in a secure way using the homomorphic encryption. How, if you ask? Because in order to train these models, we need to have a large amount of data, but these large amount of data should be not entirely visible to these model trainers, which would actually create a threat to the security of our data. So without actually revealing what the exact data is, we can use these large amount of data to train these ML and AI models, which is actually a great thing. It provides a secure environment for both the AI and ML model trainers as well as the users' data. So, like this, there are many applications of homomorphic encryption in various fields. Let's look at an example of homomorphic encryption in real life. Imagine there is a hospital which maintains its patient records in database, and for a particular patient, the doctor needs to perform multiple diagnostic tests to determine whether that particular patient suffers from a certain disease or not. But the catch is, these diagnostic tests can only be done by a third-party cloud service provider. So in this case, the patient sensitive data should not be visible to the third-party service provider. So in order to prevent that from happening, the hospital will follow the homomorphic encryption process as follows. First, that particular patient's medical record would be retrieved from the database, and consider it would be in a plain text format. So that plain text would be first encrypted using the public key, which is known by everyone. After the encryption process, the ciphertext would be sent to the third-party cloud service provider. So now the cloud service provider would apply the harmonic computation functions to perform the diagnostic test on the encrypted data. And then the cloud service provider would perform the homomorphic computational operations on the encrypted ciphertext, and the output would also be a ciphertext. So now the hospital officials can decrypt that ciphertext and actually see the results of the diagnostic test and determine whether the patient suffers from a certain disease or not. So throughout this process, the actual data of the patient is not visible to the third-party cloud service provider, which was our ultimate aim. So this is a practical use case of homomorphic encryption in real life. Let's move on to types of homomorphic encryption. There are three types of homomorphic encryption. First is partially homomorphic encryption. So what is partially homomorphic encryption? It's a type of homomorphic encryption which allows to perform either addition or multiplication on a plain text. So either addition or multiplication can be performed, but not both at the same time. So this is called partially homomorphic encryption. Let's move on to the second type, that is somewhat homomorphic encryption. In this method, we can apply both addition and multiplication to the plain text simultaneously, but the catch is we can do it only for a limited period of time or for a limited cycles. And the final type is fully homomorphic encryption. And the final type is fully homomorphic encryption. So this method allows to perform both addition and multiplication operations on the data or the plain text as many times as we want. But the catch is it is computationally expensive, meaning it takes a lot of computational power to perform the operations. So it's comparatively less used in practical life compared to the other homomorphic encryption types. Limitations of homomorphic encryption. Homomorphic encryption methods are computationally expensive, meaning they require a lot of computational performance to apply these operations on the data, which makes them slower than the normal encryption models. And it also requires large ciphertext, so it leads to necessity of more storage and network capacity. It is complex to manage and implement, but still it is in the optimization phase. It's not fully optimized. Conclusion. Ongoing research focuses on making homomorphic encryption faster and more efficient, meaning researchers and scientists are still finding better ways to implement homomorphic encryption model to make and execute much more faster and in efficient way. Also, researchers are trying ways to integrate homomorphic encryption model with artificial intelligence and cloud-based services for secure analytics due to its end-to-end privacy policy. Also, Homomorphic encryption is also used in privacy-preserving machine learning models and blockchain security. Finally, it is also expected to play a major role in post-quantum cryptography era. And that's all for the presentation. Thank you.